Thank you. Thank you so much for having me here. Super excited. I imagine most people haven't heard of Bill.com. We like to say that we are move more money than Square, and you probably heard of them. So we are a B2B payments platform. And so today we're going to do kind of maybe somewhat of a deep dive into a machine learning, deep learning problem using computer vision, something that was a very interesting, very novel technique back when this was released a few years ago. And I hit the green button? Oh, okay. All right, awesome. So at Bill.com, we process lots of payments, and we do that through analyzing documents, generally PDFs or images. And so a lot of these images, you can consider them as completely unstructured data. Sometimes they're just, someone took a photo on their cell phone of a receipt or of an invoice, or they got it through their fax machine or something like that, So we're used all across the country, and so we offer all these kinds of services for, making it easy to make payments. There are a lot of techniques out there to analyze documents, such as OCR, or optical character recognition. And so I'll provide a brief primer on that, and hopefully get a very good motivation as to why we wanted to build a homegrown model in-house. I'll go through some of the building blocks for doing that, and then end with some results. Okay, yeah, so we are, a payments platform. Probably haven't heard of us. Again, we move lots of money around, heavily regulated industry as well, so we have to be very careful with PII data, how we process that, how we build models on top of PII data as well. And a lot of that is, I'll share, all the invoices that are in this presentation are fake, so there's no user data or anything, but it's for illustrative purposes, at least here. So here's an example of an invoice that might come across, and let's say you're a fresh data scientist that joined the team, and you're like on day 0, you're tasked with trying to build an algorithm or a model or some way to extract fields from this document. To make a payment, let's say we need just 2 or 3 fields, who you're paying and the amount, right? And so you might consider what are different types of algorithms that might be able to analyze this type of document. Considering this is an image or a PDF doesn't really matter. Let's just say you don't have the text initially. But already you can imagine there is some nuance here. So if you just look at where the total is, that one of the very important fields to get right. In this particular invoice, it's there's like a amount that's crossed out, and then another amount to the right of that. So there's quite a lot of nuance to a problem that seems fairly simple or straightforward. And so you can on that day 0 or maybe day 7, once you've looked at some data, gotten yourself you have your maybe some PII data set in some clean environment, so you're able to start modeling. You might think of perhaps starting with an OCR type algorithm. So OCR is a method that's been around for decades now, actually, I think 30 or 40 years, of just finding all the characters in an image and then telling you what the characters are and where they are. And there's more, obviously now there's more advanced OCR algorithms that are based on deep learning as well, that extract not just the character, but the words and the phrases and the paragraphs and all those things, and the locations of where they are. And so if you have an image like this, and let's say you're again focusing on the on extracting the amount field, you pass that through your OCR algorithm. That's just going to generate let's just say a text string of that whole image. In that string, at least for that image, you have something that looks like total USD with some white space and then the amount there. And then you will probably work on developing an NLP algorithm to extract the amount itself. Okay, and so this starts to show one of the drawbacks of this approach is that there's these 2 steps, 2 black boxes. One of them, your OCR algorithm, which is generally open source, or you're going to use a cloud service provider like Google or AWS to provide that, and then your NLP algorithm that sits under that. But if you spend all your work tuning and making the NLP algorithm as good as you can get it, using deep learning or whatever, you're still going to come up to a performance ceiling that's as good as the OCR algorithm. OCR algorithms, they're quite strong, but they're not perfect, even for English-based documents, and they fall off a cliff when you start to get to other languages. Let's say you're processing international payments like we are. We get invoices from all around the world, and so we can't always just rely on a very strong, very powerful OCR algorithm. So that's one of the downsides of having to rely on this kind of two-step process. Okay, so here is an example of a particularly challenging, and it's even more challenging because of how how much contrast there is in the image. But for this amount, and I've given this talk also during COVID, where everyone was on Zoom and trying to raise their hands of what the amount was. So it's cool to do this in person. If you think that this is $156, please raise your hand. Okay, and if you think it's $456. Okay, good. So it's about 50-50, which is as designed. It should be very ambiguous what this is. Now, if you roll back the image, oh, sorry. You throw this into an open source OCR, such as Tesseract, and Tesseract believes this is 156. But if you roll back the invoice some more to give more context to what the amount is, you see that it was, it's obviously clear, right? It's 456. So OCR algorithms, especially when you're focusing on the key value pairs, tend to focus on one particular value compared to the key, where we notice a lot of patterns in invoices, especially for the amount field. Amounts are, the amount to pay is usually repeated. Sometimes it's big and bold, different colors. These types of nuances tend to get lost using through the OCR algorithm. There's other patterns as well. So here's an example of an invoice template. And so in this template, if you focus on the invoice number, you notice that there's a pattern, 00 dash, and then a 4-digit number. OCR is kind of one shot. You're going to take an image and then run it through and then get your text. But if you're starting to think about building some end-to-end solution that's using the full image, so using computer vision, not just the text, then those models can learn patterns through those templates for your user data. Another obvious pattern is the name, the vendor name in this case, or the merchant name. Because of the invoice template kind of stays static for particular vendors, and it's related to not just the text, but the image, the pixel, the colors, the fonts, all that, the size and all the orientation, then that pattern can be learned as well through an end-to-end solution. Here's a particular additional motivation to use an end-to-end solution. So I'm pretty lazy. I don't like post-processing results. If you're extracting, for example, dates for using text processing, the dates can come in a variety of different formats. And some of, there's open source libraries to clean that up. But there's also a variety of different ways that, not just US-based English presents dates, but also Europe-based English and then other countries as well. So one of the nice things about having an end-to-end solution is you don't have to do post-processing on the text itself once it's extracted off the page. You can just predict like the month and the day and the year. So from the input being the image, the output being what is the month, the algorithm, if it works, learns the representations of all the different ways dates are represented in the data set, right? Including if you have international invoices, it will learn those that variety as well. So whether there is the words, the month as words, shorthanded like JAN for January, whether the day comes first and the month comes second for European invoices, and I think any non-US based invoice, and all those things. So when you're being able to do that end-to-end algorithm where the output is just the month and the day, kind of saves you from having to do that post-processing, which also can produce errors, right? That's not foolproof as well, so you may lose some accuracy on that as well. Okay, I'll pause there for any questions so far. Okay, cool. Oh, okay, yeah. Oh, yeah, yes, go ahead. That's a great question. What about when images are rotated, skewed, sheared, things like that? So in computer vision, there's a lot of image augmentations that are very powerful for building computer vision-based models. For example, when you start with your input data, you can rotate it randomly by some number of degrees. The answer, the output, what you're predicting, is the same. So in this case, if your input is that image and your output is, I don't know, $125, let's say there's a $125 invoice, rotating it doesn't change the answer. It's still 125. And so you can, I mean, in some ways, generalize by adding those rotations into the augmentations or shearing or adding a noise to the image as well or blur. There's a variety of different augmentations you could do to the image, which is actually a very powerful technique and what helps during training to help the model generalize across, you know, many millions of invoices. Okay, so that's a great question. So the question is if does the OCR output a top K, I think, per character or per word of possible likelihoods? Like in the example, maybe the second one was 456 and the first one was 156. It does. There are, I think, I can't say all OCRs, but the ones that we deal with do tend to give you like the top N number of likely strings and their confidences. But you're right. There is some added complexity when you start to deal with those. First, what we've seen is the confidences coming from the OCR algorithm aren't terribly accurate a lot of times, and there's not a lot of nuance. It's maybe like 1.5 and 0. So like there's not a lot of nuance in the confidences. But also that 156 might come back as a 1 confidence, and then maybe 456 as 0.5 or so we're not sure what to show the user. Maybe you can show a drop-down menu, right, of possible likelihoods. But we like in our side, we like to automate and try to at least for the highest confidence predictions, try to not have any user decision being made. So we found this. So yes, OCR does have that. We haven't actually used those types of confidences. We tend to just use the top one for our OCR-based models. For the image, so this is an image based model, just relying on computer vision. In this case, there are confidences output as well. Those tend to be also very useful to tell you how likely that answer is correct. And that can also I can share. Also bubble in kind of different possibilities for what the answer might be. But those are good questions. Oh, yes, go ahead. Yeah. So with misalignment related to the image augmentation, you can rotate the images, let's say 5 degrees even. Well, the idea is that because this is an end-to-end computer vision algorithm, and you're training with those augmentations in it, so the algorithm itself has to learn those representations and the orientations of the text. So if you rotate 5 degrees and the text is coming in kind of like this, the model has to learn that delta, I guess. Even going beyond that, you saw with OCR approaches, when you're doing NLP algorithms, you tend to look for keywords like total invoice, USD, things like that. Those keywords aren't part of the training of this at all. It's really, and I'm getting a little bit ahead, but it really is the input is your image at the pixel level, and your output is the answer, 456. We're not letting there's no information related to what the keys are, whether this invoice has the word total USD or USD or whatever. The model has to learn all those as intermediates, right? For if it works, if the whole thing works, it has to learn all those representations for the keywords it's looking for, and also for any orientations that are off, I guess. Okay, so let's move forward. So, this is an ML conference, of course. So I don't have to dig in too much to supervised learning, but suffice to say, we do need label data, and then of course with supervised learning, we have and we are using kind of a black box algorithm, which is rooted in computer vision. So one of the most famous image-based computer vision models is AlexNet. It kind of spurred a lot of the growth of deep learning for computer vision. So it's shown here at the bottom. It is a 200,000 parameter or so model algorithm. It takes as input 256 squared images in RGB. Oh, sorry, 200,000 input parameters. That didn't sound right, because the model is 60 million parameters. So there's 60 million parameters in the algorithm. It's a combination of convnets and actually some dense layers. So this is now 10 years old. And the important thing to note about these is that the number of parameters is way larger than the number of inputs, even at the pixel level. So this kind of screams to you that this needs a lot of data to learn anything. And this was made famous training on ImageNet data sets, and those are large. I think 100 million images. And then these are my kids here on the left. So in supervised learning, you tend to always have predictions as output, whether you're doing classification or whatnot. So just going briefly about the two main building blocks. So we have convnets here, convolutional net layers. So these are very powerful for computer vision tasks. You see kind of what's happening in terms of the math in the animation here. There's this rastering that occurs, and a combination of nearest neighbor pixels that in this case are summed together through a parameter that's learned. The parameters are learned, and then output into the next layer. And these are 2D, right? So you're rastering in 2 dimensions, just to make it simple, because we're dealing with images. The way you can imagine it, if you're not familiar, is that why these are powerful for images is because of that nearest neighbor interaction of pixels, right? In this case, you see the 3 by 3 that's occurring in that first layer. When you think about images, if I change 1 pixel value of an image, it's not going to change what's in that image, right? And so there's that notion of the nearest neighbor convolution in this case, but it's really just a summation with multiplying with weights. So that's kind of the CNN. That's again very powerful for image tasks. Okay, the next building block is recurrent nets. Now this is a little outdated, but we still use them. They're still powerful, especially when we don't have huge amounts of data. We're having to train huge amounts of or super large models. But in this case, recurrent nets are still very powerful. You have a time, in this case, time dependence information that can flow through at different time steps. Time being arbitrary. In our case, it's actually character steps, which I'll share, I think in the next slide. But the idea is that the predictions from prior time steps or from future time steps, that information can flow into your existing prediction, which is incredibly important for text, especially character level text representations. So I want to combine that and kind of share what the model looks like. So if you're familiar with captioning type models, this is actually a very similar architecture, but utilized here in a very different domain, let's say. So you start with your raw image as your input. High resolution, because if you brought it down to 256 squared, you couldn't see any of the text. So we have a high resolution image as input. You have your convnets that work, and this model can be start with the pre-trained models, something like I don't know, Inception or VGG or ResNet. It doesn't really matter. What's important though is the output being this one-dimensional kind of context vector, or something that gets flattened to a context vector. If you're familiar with autoencoders, it's the same kind of idea. There's the information that is encoded or embedded into that vector embeds it's the information that's important for the subsequent models to process the image. and there is an interface from the context vector to the RNNs that help kind of, I don't know, guide particular sets of neurons from early, the first time steps to later time steps. We have a fairly simple RNN architecture that's a GRU actually, and then the output is character level, the character level predictions. Because I was saying that the output is the answer, $456, but these can be of arbitrary length and of arbitrary characters, and you can't classify, you couldn't classify each one independently. So we classify at the character level, so what the first character is, second, third, etc. So this is actually what the raw output looks like, and you can compute the confidence as just the multiplication of the top scores. One nice thing about character level representations is you can really define the dictionary. So for numeric amounts, our dictionary is numeric, and for alphanumeric, you can add the alphabet there, and etc. One of the nice things or benefits of this approach is, compared to OCR, is that if we expect a numeric answer, like a 0 can never be represented as the letter O or a 1 as the letter L, because it doesn't exist in the dictionary. The dictionary only has the allowed characters. So that's really nice. That's one of the benefits. Again, less post-processing. Even simpler, again, for the months, there's a month, I guess for dates, there's only 12 months in a year, 31 possible days in a month, right? So that's just a simple classification. And then taking care of the arbitrary lengths, we just have an end token. Very similar algorithm to captioning. Okay, I'll pause here if there's any questions. Okay, cool. So the rest of this is just sharing the results. One of the cool things is because we're utilizing deep learning, we can monitor what the model's learning at intermediate steps. So again, for the amount, this is what the loss curve looks like. At the top, and here, it's a little funky, but there's 3 columns: the actual, the prediction, and the loss. So really important just to compare the actual to the prediction. Early time steps, it's just noise. Okay, one of the first kind of things that it learns, if you compare the actual to the prediction, it learns 2 things pretty early on. One is the sense place, that it's a decimal and then 2 digits afterward. And then the other thing that it learns is the length of the amounts. So it's not really getting the characters just yet. It's just kind of learning, okay, this is the length. It's a 4-figure amount, it's a 2-figure amount. And then the notion that there is the sense place. Okay, later on in training, you see that it's starting to now get the characters. There are some, now it's learning the OCR, so there are some OCR errors, kind of classic OCR errors, is a 3 and 8, stuff like that, is a 1 and 7. And then later on, towards the end, it's getting the full field. Okay, so I have some of my own, invoices, receipts. So here's an example of an Amex bill, and you can see that it pulls the amount and the dates with high confidence. Here is an interesting one. So while this was trained on single page, you can apply it to multi-page. The way we do that is you can score each page independently and grab the highest confidence score of the full 5 pages, and that is your answer. What this is telling us is that when there is a low confidence, let's say amount, let's say 0 confidence amount, it's telling you that there isn't an amount on that page. And then, so in this example for PG&E, the amount appears on the first page, and that's the highest confidence prediction, right, as you score that independently. So it's telling you, what page it's on and what that value is, which is cool because this, we can apply this to multi-page invoices. And here's a receipt, so fairly unstructured image, of course, and with the extracted output. So okay, what about the locations, right? Because we also want to share kind of to the user where these fields came from. So we go into kind of explainability. So if you're familiar with explainability, it's very challenging to do with deep learning models. One of the, I guess, brute force ways to do it is through rastering. So you break up your image into blocks, and you take each block and you just grayscale it out, and you score the whole thing. And so and then you have your prediction and your confidence. And as you do this, there's 3 boxes where the the prediction is different, but also the confidence is very low. And those 3 boxes correspond to the location around the amount. So as you block that, the prediction and the confidence changes. The confidence being the very important thing. So this kind of proves out our earlier discussion of utilizing the full image, not just one location. So going back to this Amix bill, the amount is in 2 different places. And when you do that exercise of rastering, you find 2 areas where the confidence dipped as you blocked it, right? Again, going back to explanation, what part of the input is most sensitive to your prediction? And so these are the 2 areas that were most sensitive, had a lower confidence, and those are independent of each other. So in other words, this is a very interesting technique. If one of these areas, I mean, this is a very clean image, but if one of these areas was scratched off or torn apart, the model will pick up the amount from the other and vice versa. Okay, yeah, so I'll stop here, and I don't know if you all have any questions as well. But yeah, thank you for having me. Yes.
Hi, thanks for the talk. Can you describe a little bit the process of how you got the data and data labeling? Because I guess that the appeal of doing this like end-to-end from image to amounts without the intermediate OCR step and the pre-processing and all that cannot really be applied by many companies that don't have as many millions of invoices labeled. So can you discuss a little bit that?
Yeah, that's a great question, and you do need a large amount of data. We're still using transfer learning, so we're not training the computer vision model by scratch. We don't need hundreds of millions, but we still need on the order of 1 million or millions. For labeling, we're at Bill.com. Bill.com's been around for a long time. The product before required users to enter these things themselves. They would upload an invoice and then enter in all the fields themselves. So they're kind of our training data in a lot of ways. But we've also noticed that sometimes they enter in things that don't appear on so this is now getting to the nuance. Let's say there's a discount they got over the phone. They apply 20% discount. So that amount they enter doesn't even appear on the page. And so you can also utilize third-party annotation services. All the cloud service providers have them. They're a bit costly. But I do think because this is transfer learning, with all the augmentations that you can apply, you can get pretty far with like tens of thousands. That's kind of where we started, like tens of thousands in terms of volume. Really get to, this is like way amazing. We're beating all the cloud service providers in terms of accuracy. When you get to like the millions range of volume, you can get probably like a POC out with orders of magnitude less. Right. That's a great question. So, this was released about a year ago. And, like you can imagine, you retrain it with some cadence so that you can, discover kind of newer templates, right? Newer keywords, maybe different languages, maybe your company or you have some growth in Asia or, even in the UK, like, that's still English-based, and in fact, a lot of invoices are English-based anyways. But sourcing them from different countries does yield very different accuracies. And so yeah, so kind of the generalizability of this is important, but we've seen that it's actually very robust. So you need, I think, kind of when you train this initially, you do need enough variety, enough diversity. For example, if all of your training data is clean, and this is actually another strong suit of Bill.com. I mentioned our customers are from all over the country. middle America, getting faxes, getting invoices in the mail, taking photos of them, uploading them, things like that. So we do get a lot of, you can consider very difficult cases where if you just have very clean, very, very straightforward templates, you may not need this. This might be too heavy, right? You may need something, or maybe a very simple solution might benefit. But we noticed that we needed something that could apply to kind of the diversity that we have of, different images, image quality even, all those things.
My question was, how do you get the date formats? Because, how do you do the autoencoder in your architecture?
Yeah, so from the label data. So as an example, if the user, 5 years ago was entering in, this is the month, like this is my invoice date, this is my due date, given an image, given an invoice, that is now the label data that we use. In the example of predicting a date, let's say the invoice date or the due date, you can convert that to a simple classification problem where it's just a dense layer at the end of your context vector, and one dense layer that's 12 size for your 12 months, for invoice date. The other one that's 31 for your 31 possible dates, and then you can ask, well, what about if it predicts a date that doesn't exist, like February 30 or right? Because it potentially can happen. But it learns from data. If you give it enough data throughout the years, right, a large volume of data, the model learns that those dates are never predicted, and then potentially we haven't seen them show up. And so that's how we get the date, and you could do that for multiple dates. The idea is that you have that label per image, right? So you have your month, day for in year for invoice date, the same for due date, maybe some reconciliation, and maybe I don't know how many dates you're predicting, but the model has to learn, from at the pixel level, what the answer is, right? What that prediction is. So it has to learn all the intermediate, like the formatting, looking for keywords, looking for, is the field to the right? Is it below? Maybe it's off center. We've seen that. Sometimes the date comes in with like, the week, like Sunday, comma, 12, OCT, comma, the year. So there's so many formats it has to kind of deal with from the pixel level to the all the way down to the classification of, which of the 12 months is it. So, so it's a tall task, but that's where I think deep learning was very powerful in this kind of methodology. Yes.
So I just wanted to ask that it doesn't, correct me if I'm wrong, but it doesn't look like the model is understanding that the end result you're trying to predict is a number, because in some cases it's predicting like a double decimal point. So do you have any rules that you do after this, or what sort of loss function are you using to not ensure this, or something along those lines?
That's a great question. So you're right, because it's predicting at the character level, it's character level classification, you can have 2 subsequent characters be decimals. But what does that really mean? It means for that classification, the decimal character had the highest probability, right? Of, let's say, for amounts, there's, I think, 11 or 12 possible characters. So the decimal had the highest one. And then the next one, the decimal had the highest one. But when you look at the confidence score for that case, it's very low. So the confidence is going to be close to 0. Whereas for an amount that has a very high confidence, let's say closer to 1, it's much more confident that that is the answer. When it predicts like garbage, it's going to have a very low confidence score, close to 0. And then on the product side, when we have low confidence scores, we don't do any automation. So we found that it's incredibly powerful, not just to have the prediction, what is it trying to predict, but also the confidence. And you can get that from, like you mentioned, from loss, kind of the loss function. So I believe this wasn't a fancy loss function. I think it's just multi-class SGD or something. Or sorry, I'd have to look at the exact loss function. But the idea is that it's probabilistic, right? So for every class, the probabilities sum up to 1, right? And so if you, and the confidence is you multiply each one, the highest score, and you multiply each one. So if each one is close to 1, then the total confidence score is close to 1. But if each one is close to, I guess the smallest probability would be 1 divided by 12, right? Then you multiply 1 divided by 12 by the however many characters there are, that's close to 0. And so that's why you can have a prediction that looks kind of like garbage, but it's really the confidence score that tells you the model's, if the model's saying, hey, the amount's not here, I can't find it, or whatever the case is, I'm not sure of what the answer actually is. And so and then we use that, of course, to not do automation. And the way that you really look at that is you plot, confidence score versus the accuracy, and you should get some monotonically increasing function. So as you get to like 0.99 accuracy, 0.99 confidence, your accuracy should be 0.99. You can, of course, normalize that. So you can normalize your confidence to a probability, and then 0.99 means you're 99% likely that that is the right answer. And that can help with automation if on the product side they say, well, we can forego 1 in 10,000. And so your threshold will be, 99.9, 0.49s, right? To have 1 in 10,000 be in error.
Good talk. So I have a question. You mentioned about image data augmentation during training. Did you notice any problem? Because if the total amount, let's say, appear at the very bottom, if you clip it out, you might have problem, right? So my question is, can you elaborate on training time augmentation versus inference time? Like, is there any difference during?
For time, like as in latencies?
No, like the kind of image pre-processing you apply during the training versus during inference.
I see, yes. So I mean, we obviously don't apply augmentation to inference. It's just really to like fluff up the training data. But you're right, if you rotate too much, you might clip things. You can also imagine where you rotate, but also how you describe it, you kind of zoom out where the corners are still within your rectangle. Because your input size is fixed, right? During training. Your input size is like page 8.5 by 11, let's say. So if you rotate, let's say you want to rotate 25 degrees, something massive, 25 degrees or 30 degrees, then you may zoom out so you're not clipping any information, but everything gets smaller. And there's a limit to this, right? For example, this isn't robust enough to deal with 180 degrees or 90 degree rotations. Like we didn't build that augmentation in. There's a lot of open source like orientation detectors out there. So if someone uploads in a PDF that's rotated 90 degrees, we can detect that orientation with another service and then rotate it back and then send it to these algorithms. So we didn't deal with like the right angle orientations. We really wanted to deal with like when it's slightly rotated. One of the nice things, I mentioned it kind of fluffs it up because if you don't have a large amount of training data, you can artificially increase that with augmentation without having to, the label stays the same, it's your input that's changing. Okay. But there is a limit to how much you can rotate. But we did find the rotation is one of the most important augmentations you can add for computer vision. So like, but you can't do too much. I think 5 degrees was our limit, maybe 5 or 7 or something like that.
Okay, thank you.
Yeah. So I'm wondering, related to some of the questions that we've had before, in some cases in particular with the dates, so it shouldn't be possible to know whether it's the month or the date goes first unless you have actually seen, for example, the logo of the company in the invoice before, and that's on your training set. So how do you handle like new companies or invoices that you haven't seen before as of the ambiguity of the date? Do you add extra context information, such as, for example, the email domain of who sent it or where it comes from, or?
Yeah, so we don't. So actually for this model, really just is the image, but you can imagine incorporating more information like you mentioned, the language it was encoded in perhaps, or even the location help. But you're right, if it wasn't seen in the data before, it wouldn't have any understanding of it for new data. So in our training, we have international invoices. We haven't really dug in to understand, when it picks up like the days first compared to the month. What we can guess is that for those invoices, they're likely European, and there's likely something about the European. I mean, European invoices tend to be very, even for UK-based.
Yeah, or maybe the company's GmbH instead of the US way.
Exactly.
My follow-up question was, have you tried or do you have plans on trying, but maybe it doesn't make sense because you mentioned your error rate is close to 0, so transformer-based models for these?
We haven't. That's a great question. At least for these. So we do have. I mentioned the OC. A lot of this talk was like saying how we're going beyond OCR, but we do have OCR-based models which do use transformers like BERT models and things like that. For this one, the size of the kind of that GRU, it's actually not that large. The CV part of the model is like, I don't know, 20 million or 25 million parameters, and then the GRUs maybe like a couple million parameters that kind of stacks on the end. From my limited experience with transformers, from what I've seen is that they work really well when you have large amounts of data and large models. So you need a lot of parameters, right? And so to train large amounts of parameters, the parallelization is what helps with transformers, whereas like RNNs are very sequential. You can't predict at time 0 without predicting first your t minus whatever all the way up to t0, right? So it's very like linear based, and transformers are kind of drop that completely with attention, right? And so they're more parallelizable, which helps kind of their size grow enormously, and then you get these kind of really cool models now. But in this case, that part of the model is not that large. I don't think transformers will actually improve it at all, but we don't know. We haven't done that study.
Great. Awesome talk. Thank you, Eitan.